This is Britt Kessel with another example video. In today's video, I'm covering example 1 from section 7-6 in the SavvasRealize Algebra 2 textbook. The goal of today's video is to understand phase shift as a horizontal translation. Okay, so remember how when we were covering this equation, I think I stole this from 7-4. When we were dealing with this equation, we were talking about how this c value is a horizontal translation because it's being added or subtracted from the x, right? And we called it a phase shift because it went to the left or to the right. Now notice the structure of this equation has your phase shift inside of a set of parentheses being multiplied by b. All right, that's going to be a big deal. Oh, Lord. Here in just a moment. So in part A, it says, how does changing the value of h affect the graph of y equals the sine of x minus, or 2 sine times x minus h? So when we have our sine function, Savvas actually has a really nice slider bar here, which is good. It's good to see. Okay, so let's talk about what things are doing. Here's pi, pi over 2, 3 pi over 2, 2 pi. So the different parts of the equation, right? The sine graph usually bounces between 1 and -1. This 2 is making it go between 2 and -2. All right? So usually, I'm going to do the red as the parent function. Usually it goes 0, 1, 0, -1, 0. All right, so this is your sine function. All right, now when we have the 2 in here that's in front, all that it's doing is it's making everything go up to 2 and down to -2, right? It increases your amplitude. And so your sine function looks something like this. All right, so the green here is y equals 2 sine x. And so by now you should be comfortable with that idea. So now let's talk about h. Let's assign a value for h. You know what? I'm not going to assign a value for h. I'm going to call h some amount, some portion of pi over. For the sake of graphing, I'm going to call h pi over 2. So when I subtract that pi over 2, what we're doing is we are taking these anchor points and we are moving them over by pi over 2. Now, if you look at my scaling on my graph, do you see how from 0 to pi over 2 is one box or one tick mark? That's the same thing I'm doing here, is I'm taking each of these anchor points and scooting it over by one tick mark. Now notice I'm doing this scoot, that's at 5 pi over 2 by the way, I'm doing this scoot after I've done my stretches or compressions. Alright, you always want to translate last when you're dealing with any form of graphing transformations. So do you see how this blue graph is the same as the green graph? It's just everything's scooted over by pi over 2. Now what makes it confusing for people dealing with the sine function is, this thing still goes. So a lot of times their graphs will include like this part here where it starts coming back down again, right? Because these graphs go on for forever from left to right. It's just moving it along. So it doesn't always show the same iteration of the curve, and so you have a hard time seeing it. All right, so now let's look at what it does here with b. Okay, so here on b, I'm going to go ahead and draw my handy-dandy little graph paper. Now the 2 is no longer on the outside of the sine function for b. The 2 is now inside the sine function being multiplied to the x minus h. And so you guys have learned about that too, as acting as our b value, which talks about the period. What's happening is it's saying, sorry, that's a -1, is it's saying that the sine curve is happening twice inside one iteration. So let's show you that. Okay, so again, the red is just our parent function, so you have something to compare it to. So this is y equals sine x in red. So now let's look at it with the 2. So y equals the sine 2x. All that that's saying is that each of these distances from the y-axis to these points is cut in half. Because remember, to find your period, you do 2 pi divided by b, which in this case would be pi. So this sine curve iteration has to occur before pi. And so in this same 2 pi section, look at what happens. Now you have the sine wave twice in that same section. That's what that 2 does. Alright, so now if I subtract h from inside of there, say that I do a sine of 2 times x minus, I don't know, let's do that pi over 2 still. Keep it spicy. That's saying that I would move each of these anchor points over by pi over 2, so over by 1 block. So because this one's at the halfway marker here, it would be at the halfway marker here. This one would go here. This one would move a marker over here. Do you see how difficult it can be here? So everything's moving over 1 marker. So I did the first one, second one. Now this one would go here. This one would go here. There we go. Now I'm getting that pattern. And so this is where I was talking at the very beginning of starting to graph this stuff. And I said it might be nice to have some kind of token to move. Because you see how there's 5 anchor points for every single iteration? So if we have a horizontal compression, which is what we experienced with this 2 here, right? It made 2 of the sine curve happen instead of 1. Then we end up with 10 anchor points and we get a little flustered. So I recommend, if you're graphing this on paper, having those anchor points, because these graphs can get a little bit hanky-panky, right? But just remember, when it moves, or when it says minus a number, it's going to shift to the right, and when it says plus a number, it'll shift to the left, by however many units you have. The other thing worth noting is the format of this equation. Do you see how this x doesn't have a number in front of it? It has a parenthesis and then whatever number was there. So what that means, like for part B here, is we have to divide that 3 out. Like we have to factor the 3 out, and that'll change your phase shift. Our phase shift on that part B is not 3 pi over 4, so just be ready for that. Alright, so let's try graphing this out. So for part A, our phase shift is pi over 4. So that means, like, it's a plus pi over 4, so that means it's going to be scooting to the left by pi over 4. So what I'm doing is I'm making sure that I give myself enough room to to deal with that. Alright, so pi over 2. So I'm just going to go through, and these are my 90-degree tick marks, and I'm going to put little subticks in there. And so each of these subticks is worth pi over 4, right? Because it's half of a pi over 2. So those blue tick marks are there just to help me see those halfway markers as I graph. Now remember, the cosine is the graph that looks kind of like a U, like that. And normally it goes between 1 and -1, but right now this one has an amplitude of 3. So instead of putting extra ticks on, well, I can. But I was just going to label it 3 and -3 just to keep things clear instead of 1 and -1. So understand this is a vertical stretch because of this 3. All right. So I'm going to go ahead and draw the parent function with the 3 in there, and then I'll do my shift, I think. All right, so remember it starts at the top, goes down here, goes to the bottom, oops, goes back to here, and then goes back to your top. And so this is our beautiful parent function. Okay, kind of beautiful. I don't know how to draw. Now I'm putting some stuff back in the negative direction just so you can see what's happening that way as well. So don't be too freaked out by the fact that there's stuff here on the negative side. You know what? I don't think I want that, actually, to show you the difference. Sorry, I'm indecisive. Okay, so now we've dealt with the 3, right? That was our vertical stretch. Now we're dealing with the pi over 4. So again, because it's a plus, I'm going to the left. It always feels backwards. So each of my 5 anchor points is going to move to the left by 1 of the blue ticks worth. And so it's the same V, it's just now it's moved over a little bit. So that yellow one is this one. Okay, so now with B, B's the one where I said, we don't like that because that's not written in the format of our formula that we're used to. So what I'm going to do is I'm going to come here inside the parentheses and I'm going to factor a 3 out. Okay, so 3x divided by 3 is x. And 3 pi over 4 divided by 3 is just pi over 4. So see now how it's paralleling our first 2 examples? But I had to make it parallel. I had to get that pi plus 4, or pi over 4. Ooh, Lord, I had to get that x plus pi over 4. This part right here to have a 1 in front of the x instead of the 3. And now this is ready to graph. So let's talk about what's happening here because this is going to suck to draw. All right, our amplitude's 1, so it's going to bounce between 1 and -1. So I can include that on a graph right away. We know that it's shifting to the left by pi over 4, so we'll be doing that. But the other thing worth noting is that 3 that's in front of the x. So that 3 that's in front of the x is going to be saying that there's 3 iterations of the U shape between 0 and pi over 2. Or I'm sorry, 0 and 2 pi. We're there at the end. And so that is what's going to suck to draw. And so what I recommend doing is, just like I did my blue tick marks here to cut things into half to get my pi over 4, is we're going to use blue tick marks to cut it into thirds real quick. Okay, because we need 3 iterations to fit in here. So whereas the parent function starts out going here, 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 we're going to divide each of those by 3 to move it over. So instead of being at pi over 2, it'll be here at pi over 6. Instead of being at pi, it'll be at pi over 3, which is here. This gets a little tricky, my lovelies. I should be doing these new anchor points in other colors. And so that's what I'm going to do real quick. Because it's easy to get lost in these anchor points. So remember, we're cutting this. This is 3 jumps over, so I'm just making it 1 jump over. Okay. This one is 1, 2, 3, 4, 5, 6 jumps. 6 divided by 3 is 2, so now it's only 2 jumps. This one is 3, 6, 9 jumps. If you divide that by 3, that's only 3 jumps, so 1, 2, 3. So see how I'm taking the relative distance and just dividing it by 3? This one is 12 jumps, so I'm going to make it 4 jumps, because 12 divided by 3 is 4. So instead of going long like the red one does, this one's kind of shorter, like this. So do you see how each iteration here, ooh, that looks ugly at the end there. I'm going to try to fix that. But do you see how each iteration here now just takes 4 spaces? So I'm going to repeat that pattern. So every 1 space that I have, I'm going to make it go to the next piece. So 1 space over, this will go down to here. 1 space over, it'll go down to here. 1 space over, here. Then 1 space over, here. Then here. Then here. Then here. Then there. And so now I'm going to have the 3 jumps, see? So here's number 2. And here's number 3. So those compressions, they can be very difficult for students. So remember, because there was a 3 here, I took my usual spacings and cut them into thirds. Alright, and then I took each distance from the y-axis and divided each distance by 3. And that made it to where I can copy that pattern over and over. Okay. Now this isn't my final graph. This yellow one is just the cosine of 3x. Okay, I haven't even done the pi over 4. So now the pi over 4 creates a new tick mark. I know, as if this wasn't horrendous enough. But the pi over 4 is half of the pi over 2, not 1/3 or 2/3 of it. It's half. So between each of my blue tick marks, there's now a green tick mark. That's worth half of this unit. I'm also going to put one here at pi over 4. And so that plus pi over 4 is moving each of our new anchor points over by half a unit. So this is 1/3 and the half is there. So I'm just going to go like slightly, like right there, I guess, for this one. I don't know how to make sense out of that, but there it is. This one is slightly past that one, so it should go about here. This one we know we're just cutting into half, so it'll go here. So do you guys see how everything's just scooting over? That's where these things can turn into a real pain in the tuchus for surezies. So this one's just past a half, so this one's going to go here. This one just goes to the next tick mark. The ones that are on the tick marks are the easy ones. It's these dang ones between the third and the halves that are kind of weird and make it harder to graph. And so what you could do to make this a little less stressful is you could cut it into sixths here, because I'm dealing with halves and thirds, right? So I could have cut my pi over 2 into sixths instead of like this weird little ramshackle thing, and I think that would have made it a little less ugly here. Probably something that's wise. So this one would go slightly before. And so this is where most people get stuck with graphing. So they don't know how to deal with all these different shapes. And for sure, that makes sense. So do you see how everything is just slightly shifted to the left a little bit? I always just try to pick a main anchor point that I'm comfortable with, usually one of either a minimum or a maximum, and I try to figure out where that anchor point should have been, and then you can look at the graph and kind of tell what it should look like. But there we have it, guys. That is how to understand phase shift as a horizontal translation. Until next time.